Have you ever stopped to think, as these AI systems keep making these unbelievable exponential leaps forward, what's actually stopping AI research itself from doing the same thing? It feels like the next logical step, doesn't it?
It really does. But therein lies a core paradox. And it's a pretty significant bottleneck, actually. While AI capabilities, they're exploding exponentially, the pace of the research behind them, it's still largely constrained.
Why is that?
Well, because it's still overwhelmingly a human job, limited by our own cognitive capacity, the sheer number of hours researchers can put in, our bandwidth, basically.
Right. So even while AI is, making art, writing code, crushing complex games, the actual process of inventing that AI, the really deep architectural stuff, that's still mostly us. Humans in the lab, thinking, coding, testing.
Exactly. We're the ones doing that core innovation. And traditional methods like neural architecture search or NAS, they've helped, sure, but they kind of operate within the boxes we define.
So they're more like fancy selectors than inventors.
Precisely. More like a really sophisticated selection algorithm, optimizing within a human-defined space rather than being a truly creative agent. It can fine-tune what we've thought of, but it struggles to really dream up something completely new.
Okay, so if we humans are the bottleneck, what's the way around it? Is there one?
Well, that's exactly what we're diving into today. Our mission here is to explore this really revolutionary system called ASI-ARCH.
ASI-ARCH. Go on.
And the whole idea is to shatter that human-centric limit by getting AI to actually conduct its own architectural innovation.
Okay, now you've got my attention. So we're talking AI designing AI.
We are. We're going to unpack some seriously cutting-edge science today, mostly from this key research paper that details the ASI-ARCH system.
And this represents a real shift, you're saying, not just faster searching.
Oh, absolutely. It's a fundamental paradigm shift. We're moving away from just automated optimization, tweaking existing designs, towards automated innovation. Imagine an AI that can, all by itself, come up with truly novel architectural ideas, then turn them into working code, and then actually test them, validate their performance through real experiments. That's the essence of ASI-ARCH stage.
Wow. Okay, this is where it gets really wild for me. The paper mentions an AlphaGo moment for AI architecture. Now, AlphaGo, that was the AI that made those unheard of moves in Go, right? What does that analogy mean here?
It's a really powerful analogy. Remember AlphaGo's Move 37 against Lee Sedol, the world champion?
Yeah, it baffled everyone.
Exactly. It was so counterintuitive, so alien almost, but strategically brilliant. It basically uncovered new truths about Go that even the best human players hadn't seen.
Okay.
ASI-ARCH has done something similar, but for neural network design. The architectures it discovered aren't just slight improvements. They show these emergent design principles that consistently beat the best human designs.
So it's finding new ways to build AI.
Yes. Illuminating pathways for innovation we didn't even know existed. It's like seeing a kind of scientific superintelligence emerge, but focused specifically on design.
And it's not just a one-off discovery, is it? There's something about scaling this discovery process, a scaling law.
That's perhaps one of the most groundbreaking findings, yeah. The research provides empirical evidence that these architectural breakthroughs can actually be scaled with computation.
Meaning,
if you look at Figure 1 in their paper, you see this really strong, clear, linear relationship. More computing hours put in equals more state-of-the-art architectures discovered. It's almost predictable.
So research progress itself becomes scalable, not limited by human thinking speed.
Exactly. It transforms research from being human-limited to being computation scalable. And if you zoom out, the implications are, well, profound.
Like what?
It points towards a tangible path for what you might call artificial superintelligence for AI research, ASI-4AI. AI systems that can genuinely, autonomously conduct their own scientific research and design the next, more powerful generation of AI models.
Okay, my mind's slightly blown already. This sounds revolutionary. How does ASI-ARCH actually do this? How does it run this autonomous research lab, so to speak?
It's pretty cleverly designed. At its core, it's a multi-agent system. Think of it like a little team of AI specialists working together in a closed evolutionary loop.
A team. What roles do they play?
There are three main roles, three core modules.
Let's break them down. Who's first?
First up is the researcher module. This is kind of the creative engine. It's the one proposing novel architectures.
Where does it get its ideas?
It draws on its own past experiments, its history, but also on knowledge that's been distilled from human expertise, from research papers and the like.
Okay, so it has some grounding in what we know.
Right. And crucially, it doesn't just design on paper. It directly implements its ideas as executable code.
Why is that direct implementation so important?
It prevents something they call implementation drift.
Mm-hmm.
That's where the final code might accidentally end up being slightly different from the original concept if, say, one agent designed it and another one coded it. This way, the idea and the execution stay tightly linked.
Got it. So the researcher dreams it up and codes it. Then what? Who takes the baton?
That would be the engineer module. Its job is to run the experiments, do the empirical evaluations in a real coding environment.
Okay, testing the code.
Yes. But here's where it gets really interesting. It has this very robust self-revision mechanism.
Self-revision. It fixes its own bugs.
Exactly.
Yeah.
If a piece of code fails, maybe throws an error, previous systems might just toss that idea out. But ASI-ARCH's engineer analyzes the error logs, figures out what went wrong, its own mistake, and then actually revises the code it generated previously.
Wow. Okay, that's not trivial. An AI debugging its own generated code.
It's a huge step. It means promising ideas don't get thrown away just because of a simple coding error. It makes the whole trial and error cycle much, much faster and more resilient.
Okay, researcher, engineer. What's the third piece?
That's the analyst module. Its role is synthesis. It takes all the experimental results, figures out what was learned, acquires new insights.
Then where does it get context?
It enriches its findings by connecting them to a knowledge base they call the cognition base. Think of it as a library of relevant concepts. And all this data, the results, the insights, everything gets archived in a central database. It builds a persistent memory, learning over time.
This whole process really does sound like an artificial version of evolution, doesn't it? How does it decide which designs survive or get built upon?
It is very much like biological evolution, yeah? There's a comprehensive fitness score. That score determines which architectures, get to reproduce or influence the next generation of designs.
And how is that fitness score calculated? Is it just about performance?
That's where they were quite clever. They specifically tried to address a big problem in earlier approaches, something called reward hacking.
Reward hacking, like gaming the system.
Exactly. Where the AI finds a way to maximize a simple metric, like reducing the loss function number, without actually creating a better architecture in a meaningful sense.
So it's not just about getting the lowest loss score. How do they measure the actual quality of an architecture?
They use a composite fitness function. It combines the objective stuff, benchmark scores, loss, with a more qualitative assessment of the architecture's quality.
How do they judge quality? That sounds subjective.
They actually use another large language model, an LLM as judge, they call it, to evaluate things like how innovative the design is, its structural complexity, whether the implementation is clean and correct.
Using an AI to judge the AI's work, okay?
And they did something else smart with the scoring. They applied a sigmoid transformation to the performance differences.
Sigmoid? What does that do?
Basically, it means small improvements get amplified, so they're still rewarded, but extreme outliers don't completely dominate the score. It prevents the AI from just finding one weird trick to max out a single metric, encouraging more balanced, holistic progress.
That makes sense. And efficiency. Running all these tests must take tons of computation.
It does. So they use a two-stage strategy. First, a broad exploration phase on smaller scale models to quickly find promising candidates. Then only the best ones get rigorously validated on larger models. Exploration, then verification.
Okay, so after all this, the autonomous research, the self-correction, the smart fitness function, what did ASI-ARCH actually come up with? Did it really discover things humans couldn't?
It really seems like it did, and the sheer scale is impressive. We're talking 1,773 autonomous experiments conducted over 20,000 GPU hours. Just wrap your head around that number.
20,000 GPU hours, wow. And the result?
The discovery of 106 innovative state-of-the-art linear attention architectures. That's a huge number of novel designs. And really importantly, they've open-sourced all of them.
That's fantastic, so anyone can use them.
Yep. The community can build on this work.
And how good are these AI-discovered models compared to, say, the best things human researchers have designed?
Well, the paper makes it pretty clear. These AI-discovered models systematically outperform the human-designed baselines. That includes some really strong recent models like Mamba 2.
Systematically, across the board.
If you look at Table 1 in the paper, they consistently show better performance on a range of tasks. Language modeling, common sense reasoning. It's not just a fluke on one benchmark. These are genuinely strong architectures.
Can you give us a flavor? Like, what makes them different? What are these emergent design principles the AI found?
Sure. I mean, these aren't just tiny tweaks. They represent genuinely new approaches. Take Pathgate FusionNet, for example. It developed this really clever hierarchical gating system, almost like a smart traffic controller for information inside the network.
A traffic control.
Yeah, it manages the flow between processing local details and understanding the bigger picture, the global context. It resolves a common trade-off really elegantly.
Okay, that sounds pretty sophisticated. Any others that jump out?
Well, there's fusion-gated FerNet. This one actually changes a fundamental mechanism called gating. Instead of one gate choosing between paths, it uses parallel sigmoid gates.
Parallel gates. What does that allow?
It lets the model activate both local and global information pathways at the same time, which breaks a standard constraint. It also enhances how the model handles memory, making it more controllable.
So these are really different ways of thinking about network structure.
Exactly. They're not just minor variations on human themes. They showcase, I think, a qualitatively different kind of architectural intelligence emerging. Truly novel ideas.
It's one thing to say an AI found these new things, but it's another to understand how. What did the researchers learn from watching ASI-ARCH work? What insights came from analyzing its search process, its sort of AI mind?
Yeah, that analysis is just as fascinating as the results themselves. They saw the search followed a pretty typical learning curve, rapid improvements at the start, then things start to level off a bit.
So it hit a plateau.
Well, yes and no. The fitness score stabilized, but that was actually by design. Remember that sigmoid transformation? It was doing its job, preventing the AI from just chasing one metric, indefinitely preventing reward hacking.
Ah, right. So it wasn't a performance bottleneck.
No, because crucially, the raw performance metrics, the benchmark scores, the loss numbers they kept improving steadily underneath that fitness score stabilization, the models were genuinely getting better throughout the process.
That's a really important distinction. Okay, so the AI was making real progress, not just gaming the score. Did it achieve this by just making the models bigger and bigger? That's often the easy way out.
That's a key question they looked into. And the answer was no. The performance gains did not come from just inflating the model size.
Really?
Yeah, figure 8 in the paper shows this clearly. Most of the architectures ASI-ARCH explored and settled on stayed consistently within the 400 to 600 million parameter range.
So it showed architectural discipline.
You could call it that. It wasn't just throwing more parameters at the problem, it was finding smarter designs within a reasonable size constraint.
Interesting. And what about the building blocks it used? Did it go for radical, completely new components, or did it stick with more familiar stuff?
It actually showed a pretty clear preference for established, proven components, things like gating mechanisms, convolution, stuff that has a track record. It tended to avoid more obscure or, say, physics-inspired components that haven't been as widely validated.
So it was innovative but also pragmatic.
Kinda, yeah. It mirrors how human scientists often make progress, doesn't it? Building on a solid foundation of what works, innovating on top of proven techniques, rather than just chasing novelty for novelty's sake. The best models it found really converged on using a core set of effective, known components in new ways.
Okay, now let's get to maybe the most fascinating question they asked. Where did the inspiration for these breakthrough designs actually come from? What was the source?
Right, they tried to trace the lineage of the ideas. They broke it down into 3 categories, which were first, cognition, basically. Knowledge pulled from the human expert literature, stuff we know. Second, analysis. This means patterns and insights derived from its own previous experiments, learning from its history. And third, originality, completely novel ideas generated by the model itself, not directly traceable to the other 2.
Cognition, analysis, originality. Okay. What did they find? Which one drove the best results?
The results here, shown in Table 3, are really quite telling. For the general pool of architectures it generated, cognition leaning on human knowledge was the biggest factor, about 51.9%.
Okay, that makes sense. Start with what's known.
But for the top-performing state-of-the-art architectures, the ones in their model gallery, the picture changed significantly.
Oh, so...
For those elite models, the contribution from analysis learning from its own results jumped up to 44.8%. That was much higher than in the general pool, and nearly equal to cognition, which was at 48.6%. Originality was the smallest slice in both cases.
Wow, so the very best ideas came more from the AI analyzing its own work?
It strongly suggests that, yes. For an AI to produce really breakthrough results, it seems it can't just remix human knowledge effectively. It needs that cycle of exploration, experimentation, synthesizing results, and discovering new principles from its own empirical data. That self-analysis seems key to synthesizing truly novel and superior solutions.
What an incredible deep dive this has been. We've really unpacked ASI-ARCH, this system where AI autonomously designs better AI. A genuine AlphaGo moment for this field of scientific discovery, as you said.
And establishing that scaling law for research itself, showing that innovation, in this context at least, can be computationally scaled. That's huge.
It feels like a fundamental shift in how AI research can even be done, doesn't it? Moving away from progress limited by human hours and insights.
Towards progress that's potentially scalable with computing power. It gives us this profound glimpse into a future where AI might actually accelerate its own evolution in a very direct way.
And I guess that leaves us, and you listening, with a really provocative thought to chew on. If AI can learn to innovate like this, to self-correct its own design processes for building better AI, what other really fundamental human-limited challenges could it eventually learn to scale through its own autonomous discovery?